NASA just did the impossible. They touched the sun. And what they found in its fiery atmosphere is even more bizarre and revolutionary than anyone expected. For the first time in history, a human-made object flew through the sun's blistering corona, the very source of the solar wind that washes over our entire solar system. Back in April 2021, a car-sized spacecraft named the Parker Solar Probe plunged into this uncharted territory, moving faster than anything humanity has ever built. The data it's sending back from inside our star is challenging decades-old theories and helping to solve mysteries that have puzzled scientists for generations. This isn't just a story of incredible engineering. It's a story of discovery, of venturing into a place we were never supposed to survive, and coming back with answers that will redefine our understanding of the cosmos. The first, most obvious question that comes to mind is how? How do you send a sensitive $1.5 billion piece of scientific equipment into an environment that reaches millions of degrees without it instantly vaporizing? The sun's visible surface, the photosphere, is a searing 10,000 degrees Fahrenheit, about 5,500 degrees Celsius. But the corona, the ethereal atmosphere that the probe flew through, is paradoxically hundreds of times hotter, reaching temperatures of millions of degrees. It's a mystery scientists call the coronal heating problem, and it makes the probe's survival seem like pure science fiction. The answer lies in one of the most brilliant feats of engineering ever conceived, the Parker Solar Probe's thermal protection system, or its heat shield. This isn't just a slab of metal. It's an 8-foot wide, 4.5-inch thick shield made of a carbon-carbon composite. Imagine a material that's mostly empty space, making it incredibly lightweight, yet capable of withstanding unimaginable punishment. While the sun-facing side of the shield endures temperatures up to 2,500 degrees Fahrenheit, about 1,377 Celsius, the instruments nestled in its shadow remain at a comfortable room temperature. But there's another crucial piece to this puzzle: the difference between temperature and heat. Temperature measures how fast particles are moving, while heat measures the total energy they transfer. The corona, despite its mind-bogglingly high temperature, is an extremely tenuous plasma, almost a vacuum. The particles there are moving at incredible speeds, but there are very few of them in any given space. Think of it like this. You can stick your hand in a hot oven for a second without getting burned, because the air, while hot, doesn't transfer its energy to your skin very efficiently. But if you touch the metal rack inside, you'll get a severe burn instantly. The Parker Solar Probe flew through the hot oven of the corona, not the metal rack. Still, the margin for error is non-existent. The spacecraft must remain perfectly oriented, keeping its heat shield pointed directly at the sun at all times. A slight wobble, and the delicate instruments behind the shield would be exposed to the full, unfiltered wrath of the sun, ending the mission in an instant. This requires a ridiculously sophisticated autonomous guidance system, which uses sunlight sensors to detect any deviation and fire thrusters to immediately correct its orientation. The probe literally uses the sunlight that's trying to destroy it to stay alive. Welcome to Cosmic Chronicles. We have noticed that 91% of you that watch this channel frequently do not subscribe. If you've ever enjoyed my video, please could you do me a favor and hit the subscribe button? It helps this channel more than you know, and the bigger the channel gets, the more valuable content you enjoy. Touching the sun wasn't a simple matter of pointing a rocket and hitting go. It was a cosmic ballet of gravitational mechanics that took years. Launched in 2018, the Parker Solar Probe embarked on a long, looping trajectory through the inner solar system. The key to its journey was Venus. The probe was designed to perform 7 Venus flybys, each one using the planet's gravity to shed orbital energy and bend its path closer and closer to the sun. With each pass, the probe's orbit shrank, and its speed dramatically increased. At its closest approaches, dictated by the laws of orbital mechanics, the Parker Solar Probe is moving at an almost incomprehensible velocity. It's projected to reach speeds up to 435,000 miles per hour, about 700,000 kilometers per hour. Let's put that into perspective. At that speed, you could travel from New York City to Tokyo in less than a minute. It is, by a huge margin, the fastest object ever built by humanity. This incredible speed wasn't just a side effect, it was a critical part of the mission. The regions of the corona the probe needed to study are a cauldron of extreme heat and radiation. The strategy was to get in and get out, fast. Like a daredevil sprinting through a wall of fire, the probe spends as little time as possible in the most dangerous parts of its orbit, gathering a frantic burst of data before swinging back out into the relative safety of space. Finally, after years of patience and precision, the moment arrived. During its 8th flyby of the Sun in April 2021, the Parker Solar Probe crossed a monumental invisible boundary. It's a threshold known as the Alfvén critical surface, the point where the solar wind transitions from being magnetically tied to the Sun to a free-flowing supersonic wind. It's the outer edge of the Sun's atmosphere. For the first time, a spacecraft had officially entered the solar corona. NASA had touched the Sun. So what did Parker find in this uncharted territory? The data it has sent back is nothing short of revolutionary, revealing a star that is far more dynamic, complex, and frankly, weirder than we ever imagined. First, scientists learned that the edge of the Sun isn't a smooth, uniform ball. The Alfvén critical surface, the very boundary the probe crossed, was found to be incredibly uneven and wrinkled. Instead of a clean sphere, Parker discovered that the corona's surface is full of dramatic spikes and deep valleys. This means that as the Sun rotates, the probe can find itself passing in and out of the corona several times during a single flyby, dipping below the surface into the Sun's atmosphere and then popping back out again. This discovery fundamentally changes our model of where the Sun's atmosphere ends and where the solar wind truly begins. Deep within the corona, Parker made one of its most bizarre discoveries. It flew through giant S-shaped kinks in the Sun's magnetic field. Scientists have named them switchbacks. Imagine magnetic field lines streaming away from the Sun like perfectly straight ribbons. Suddenly, one of those ribbons doubles back on itself in a sharp, hairpin turn before flipping back around and continuing on its way. These switchbacks were first spotted decades ago, but they were thought to be rare. Parker Solar Probe discovered that they are everywhere. They're a fundamental component of the solar wind. For years, a central question was where they came from. Did they form far out in space, or did they originate on the Sun itself? Thanks to Parker's close-up view, we're getting closer to an answer. The probe's data strongly suggests that many of these switchbacks are born in the magnetic funnels that form between large convection cells on the solar surface. It's like finally being able to see where a river begins by following its currents all the way back to the mountain spring. For over a century, the coronal heating problem has been one of the biggest paradoxes in astrophysics. Why is the Sun's atmosphere millions of degrees hotter than its surface just 1,000 miles below? It defies the basic laws of thermodynamics. It's like walking away from a bonfire and finding that the air gets hotter, not cooler. Scientists have proposed two main theories: magnetic waves, called Alfvén waves, that crash and deposit their energy as heat, or countless tiny explosions called nanoflares that collectively heat the corona. Parker was designed to test these ideas by sticking a thermometer right where the heating is happening. While the final verdict is still out, the data is providing incredible clues. The probe has directly observed the processes of magnetic reconnection, the snapping and reconfiguring of magnetic field lines, believed to power nanoflares. It has also found evidence for other complex wave and turbulence phenomena. While the problem isn't completely solved, recent data has helped rule out some possibilities, and Parker is providing the ground truth data needed to finally piece together how the Sun superheats its own atmosphere. During a daring plunge on Christmas Eve 2024, Parker's imagers captured something astonishing. It witnessed a massive eruption, a coronal mass ejection, or CME, up close. But it also saw something that had only been hinted at before. In the wake of the eruption, the probe saw elongated blobs of solar material falling back toward the sun. While other missions had seen this solar recycling from a distance, this was the first time scientists had ever witnessed it with such incredible clarity from within the corona itself. It turns out that not all of the material from a solar eruption escapes into space. Some of it is pulled back by the sun's immense gravity, reconfiguring the magnetic landscape of the corona. This discovery is eye-opening because it shows that CMEs aren't just one-way events that affect the planets. They are part of a complex cycle that also reshapes the sun itself, potentially influencing where and when the next eruption might occur. This journey into the heart of our star is revealing a universe far more interconnected and dynamic than we ever knew. Beyond the sheer wonder of these discoveries, you might be asking, so what? Why does this matter here on Earth? The answer is that we live inside the atmosphere of this star. The solar wind that Parker is studying is the same solar wind that continuously washes over our planet. And sometimes, that wind turns into a storm. Violent solar eruptions, the CMEs that Parker is now studying up close, can hurl billions of tons of magnetized plasma into space. If one of these storms is aimed at Earth, it can have devastating consequences. A major space weather event could overwhelm our planet's magnetic field, frying the satellites we rely on for GPS and communications. It could pose a serious radiation risk to astronauts and even passengers on polar crossing flights. In the most extreme cases, it could induce powerful electrical currents in our power grids, leading to widespread, long-lasting blackouts. Predicting space weather is incredibly difficult because we've always been studying it from 93 million miles away. The Parker Solar Probe is changing that. By directly sampling the solar wind at its source and witnessing eruptions as they happen, the mission is providing the critical data needed to revolutionize our space weather models. This will dramatically improve our ability to forecast their arrival and intensity here at Earth, giving us more time to take protective measures against the fury of our own star. The incredible story of the Parker Solar Probe is far from over. Its primary mission included 24 orbits, gradually stepping closer to the Sun. Having begun its closest approaches in late 2024, the probe will remain in this record-breaking orbit, continuing to make observations. As the Sun's 11-year activity cycle progresses, the corona that Parker flies through will change. The probe will have a front-row seat to this transformation, mapping the structure of the solar wind from the turbulent solar maximum to the eventual quiet of the solar minimum. The mission has already been extended, and while its future beyond its current phase is periodically reviewed by NASA, the spacecraft itself is healthy and continuing to gather priceless data with every pass. We are in a golden age of solar physics. We have, for all intents and purposes, built an outpost in the atmosphere of a star. The Parker Solar Probe is a testament to human ingenuity and our unyielding curiosity. It's a machine built to survive the apocalypse, flying through an environment of unimaginable heat and speed on a quest for knowledge. The secrets it has already unlocked have been revolutionary, but the most profound discoveries may still lie ahead, waiting in the data from its next daring plunge into the fire. The Sun is just beginning to give up its secrets, and we are finally there to listen.